Yeah, I just wanted to say a few words about how we're planning to use the advanced sensors to push the frontiers of one of the experiments that we've been working on for a long time, and that's the search for neutrinoless double beta decay. This is actually a picture of the core experiment as it was assembled many years ago, and this is an effort that Reina and I and the core and stupid collaborations are working on. And as you can see, this is actually, and at the time was one of the largest solution refrigerators ever built. So fundamental physics really drove some of the technology that's now becoming quite common in quantum computing, and this size of refrigerator is now something that Google, IBM, and others are trying to implement for quantum computing. So what we are trying to do, next slide, is to look for a rare nuclear decay that has never been observed, neutrinoless double beta decay. And the approach of this experiment is you grow volumetric crystals, in this case out of tellurium, and you look for this decay of tellurium into xenon. And if neutrinoless double beta decay happens, you should see the energy of the two electrons and nothing carried away by the neutrinos. What we are doing is we have volumetric detectors at 10 millikelvin, and they are read out by NTDs, neutron transmutation doped germanium thermistors. Very simple technology, and it's just registering really the temperature change in those detectors. And they are slow. So basically we get single pulses out like this. And if we see this in a single crystal and not a multiple site scattering event, then this might be a candidate for neutrinoless double beta decay. And the idea really is that we know the energy of this transition and we're looking for a single peak. Now, we've run this experiment, we have results, and we're now trying to push it further. Next slide. And the idea right now is to add instrumentation to these detectors so that we can do two things. One is to do particle ID to discriminate backgrounds like alphas and gammas, and also to reduce pileup. So we're planning to add a germanium wafer with readout to these detectors to detect the light from the crystals, so that gives us particle ID. But then, since we're also planning to investigate a new isotope, molybdenum-100, we have to worry about the pileup from two neutrino events, which are well established, and they have a much shorter half-life, and they can pile up above and around our Q value. So what we want to do is now develop technology that allows us to deal with this pileup background that can be underneath our double beta decay measurement. And this is where new sensors come into play. And we have been, next slide, we have been investigating and doing R&D on two detectors. One is where we use germanium light detectors with a bias. They're called Naganov loop light detectors. They're still pretty conventional, but they give us a good measurement of the light, but they are not very fast. The real interesting work is now on TESs, transition edge sensors, and there's an R&D effort to optimize those so that we can have very fast readout of the light, and therefore also then discrimination of this pileup background. Now, TESs have been used extensively or are being used in cosmology, but what we are trying to do is to use them on macroscopic big bolometers and try to read them out of this big dilution refrigerator with about 1,000 channels. And so the interesting work is right now optimizing TESs for these light detectors and then doing the multiplexing so that we can actually read this out. And if we succeed, next slide, then you could imagine building and instrumenting a double beta decay experiment that not only tests and probes what we call the inverted mass ordering, but perhaps even goes into the normal ordering of neutrino masses. Thanks. Questions?
I assume that the multiplexing is one of the challenges in this. What method are you using to read out the 1,000 sensors? What kind of multiplexing feed?
Yeah, so basically the starting point is to do the frequency multiplexing. So working with collaborators at Yale to do this. But the real challenge is if you go to the very first slide, actually doing this, over these distances and with big detectors. So you're starting to see all sorts of different effects instead of just reading out bolometers on a wafer chip, but actually doing this over this distance. So there are some real engineering challenges how to get this out of the fridge, and I think that's going to be the biggest challenge.
But as implemented, we have 1,000 channels without any multiplexing.
So basically, it's no multiplexing gets you to 1,000. And then if you want to grow bigger, okay.
Yeah, I guess, does that include squid amplifiers after the bolometers and everything antenna coupled to see the lighter?
Yeah, so that's all what's being tested now. And of course, the other challenge, which I did not mention, is that all of the things we do here have to be super low background. Yeah. Since basically we don't want to bring any radioactive contamination close to our detectors. So there are stringent requirements also on the TS fabrication, the amplifiers. Okay, let's move on.